Okay. So next we are going to hear about fast and flexible data structures for the LHCb run-free software trigger. So please go ahead.
So by now you've heard that we at LHCb we have fully software-based trigger, and you already learned that we need to be fast for that. So and how do we make things fast? So we have many options. First is the standard multi-threading. So for that we need to basically have all of our software to be thread safe. So that's the first step. We do task-based scheduling of algorithms. So when algorithms are only run if they need to produce an output. If not, then we don't need to spend time on that. Vectorization, we need to do, this is, we're going to heavily, I'm going to talk about it. And new architectures, you already heard about the usage of GPUs in HLP1. So I'm mostly going to concentrate on HLP2, where we do the full detector reconstruction, track reconstruction, and selection. But a lot of ideas I'm going to talk about are actually also used in GPU. So these two develop basically simultaneously, and some ideas developed for one, but also used for the other and other way around. So the ideas are not unique to HLP2, but the reason is that we do a lot more in HLP2. We don't just do track reconstruction and stop there, but I'm going to talk about the rest. So to basically give you an idea on how we do different, why we need to do things at different steps, I'm going to take you through a life of a B-meson candidate. So at LHCb, we do a lot of B physics, although we do much more at the moment and do much more in the future. So this graph will come back a few times during the talk. So what it shows is a data flow and a control flow. So you basically start with the row event, that all the information coming from the detectors, the subdetectors, and then taking that information and going through the several steps until we have a trigger decision at the end. So basically the blue arrows shows the data flow, and we go down in the control flow. So let me start with the track reconstruction here. So we get a lot of information from the subdetectors. This will be thousands of hits coming in every detector. And then we use this information to construct our tracks and particles. What this means is that we need to access data quite a lot. So for every track construction, basically for every track, we need to access the hit information from several detectors. And that means that we need to be quite fast accessing this information. For this, we develop our the data structure we use. For run12, what we used is called a key container. This is a pointer to an object. This would be a track, and every object will have a key in this container. So these are you already heard about the array of structs. So these containers are array of structures. So the access to the information is slower. So every time, imagine this is a track and it acts as a momentum. Every time I want to cut on the momentum of all tracks, I need to get this information at different places in the memory, and that's slow. The other thing is that, as I said, the containers hold pointers to the objects. So these objects are at different places in the memory. So every time I need to allocate memory to one of these objects, I need to allocate this for every object separately. So this means that we need to do memory allocation and deallocation many times, not per container, but per object, basically. So this is, again, slow. For run3, Andrea mentioned already, we are moving toward more the structure of arrays. These are more SIMD friendly, so that allows better multi-threading, and well, it's better both for vectorization and multi-threading because memory allocation is faster and data access is also faster. So you already heard in the morning for CMS that using these structure arrays are not that simple because our objects are not simply just few numbers next to each other. What we need is we have more complicated information, and also our containers grow. Basically, you don't know how many tracks you will construct in advance, so you cannot really fix the size of this. So this means you basically need to develop a layout that is more flexible to be used for our purposes, and this is exactly what we did with LHCb. We call these SOI collections. So collection is just like a vector, but it's the objects in instead of objects we have arrays in SRA layout. So in each array, we call these fields in this collection can be represented by a tag. So let's say I want to create tracks. For these tracks, I will have a momentum tag, which will be a float, and an index for it, which can be an integer. We can have more complicated things like LHCb IDs. These are LHCb specific 32-bit detector information and data. You can also have hits. This would be a vector field, and which itself is a SOA array itself with an index and LHCb ID. The only thing I need to do, create this SOA collection. I call it, give a name, and which field I want to have. So these tags basically contain all the information about the field. This will be what type it is, how is it represented in the memory. This is a float field, and how to persist it later, which I'll come back to it later. So this field basically also can have more complicated structures. Then what do we do with this? Once we create the collection, we need to be able to put things in it and read them back. Basically, the benefit of actually having these collections is that they are SIMD friendly. So we can, the way they are designed is basically one object is just a slice in the connection, so that the momentum of your first track would be first field in the first index in the momentum field, and so that goes on so on. So you just take the slack in this SOA collection, and that will give you one object. But for SIMD to be able to use more vectorization, we don't want to do it one at a time. We want to do it n at a time. So in case of a SIMD instruction with a width of 8, we can do 8 operations at once. The way we call these slices, basically, we use these proxies. So a proxy is basically represent the chunk of objects in the collection. If it's a scalar, this would be one object. If it's a SIMD, this will be n. For example, as I said, it would be 8 or so on. So when I have to put something into the collection, I can do, if it's SIMD, I can put 8 objects, and this proxy will represent 8 fields in all the arrays. And then I can just set the momentum. And if I want to read back, I can loop over these tracks, again, 8 at a time, and reach the momentum. And then the benefit here is that I can easily switch back and forth between scalar and the vector version. So if I want to now loop over these tracks, which I created in a SIMD version, but I want to call them one at a time, I can just call scalar, and this will give me one track. Now coming back to to my B meson, so once I have tracks here, or this could be particles, now I don't want to stop there. So of course I now have more information. I built the tracks just using the information from tracking stations, but I also get information from particle information detectors. So I want to, each of these tracks, I want to add some PID information to them. The problem is that our objects in event store are constant, so we cannot really add some information to our tracks. We need to create new objects that has both track information and the PID information. The reason they are constant is basically our functional framework requires inputs to be constant, such that you can do multi-threading safely. Just this is an example. So I have one algorithm that creates an output. This output is an input to another algorithm, and that algorithm will create 2 outputs, and these are inputs to another algorithm. But it will be in the case that there's another algorithm that takes these same inputs and does something else with them. So they're not allowed to change anything with these inputs, such that it doesn't matter how you run them. If you change the order of how you run them, nothing should change. And this also allows what I mentioned earlier, the task-based scheduling. So if the compiler thinks it's better for the scheduling to run one of them before than the other, because everything is constant, they can do that as well. But then what do I do? So I look at, we have 2 options. One, I can create new objects, adding both information from tracking and the particle identification. but this basically duplicates the information. I already had them somewhere. I don't really need to create a new one. Then the other option is we have we keep the original object and create another object with the new information, but then we somehow need to keep correspondence between these two. And here we have two options. One is called relation tables. We basically keep a relation between two objects and save that information somewhere. This is also the model we use for the run 2. The other is called zipping. So what zipping is basically a set of collections. So I have more than one collection. I can have 2, 3, or more. They should be same size, so that they somehow need to make sense to be zipped. They should have same number of entries. And then what we do is then, let's say I have a track, a particle ID object. I have some information from rich detector, which I call the rich info, or there could be other things. All of these have same sizes. They correspond to same original track, and we zip them to what we call a charged basic. So now this itself is an SOA collection. The good thing here is that this SOA collection here doesn't actually own any memory. It's just pointers to the original tracks, the original objects. But the way we operate on them is exactly the same, just like a SOA collection. So if I want to make a zip of my tracks and PIDs, I'll just do make zip, and this gives me an object SOA collection I can call. And then if I want to access the information, I'll just loop over this zipped SOA collection with using zip proxy. This is similar to the proxy I mentioned earlier we use for the other SOA collections. And I want to get let's say I want to get the momentum of the track. As I said, the zip carry all the information on how to get information. So I ask for momentum, which of the objects had the momentum. This would be tracked, so I will get the momentum of the track. And if I ask for PID, then the PID object here had the PID information, so that's what give me the PID information. So I don't need to change anything. The way we access these objects, the SOA collection is exactly the same when they are zipped or not. But in many cases, we don't actually just have two containers with exact referring to the exact same object. In many cases, let's say here, we selected our pion chaos and combined them into a combination that will be a B-meson candidate. And this candidate in somewhere else, another algorithm will create a primary vertices. So now I want to know which primary vertices this big candidate came from. These are obviously not these two collections obviously don't have the same size necessarily. For this, what we use is we call the relation. So we want to have a relation from one collection to something else. This can be a collection to an info, but not necessarily. I mean, you can have just one track and some information about its the acceptance information. This is not commonly done, but it's possible. The other option is to have a relation between one collection to another collection. I should mention that this is exactly same for the key container, or for the run2 model as well. So in this case, we can have, for example, a relation between particles and primary vertices, as I mentioned. We can also add some information like weight. So you'll have several primary vertices you can associate to your B candidate. And in this case, you can give them some weights to tell which one is more likely to be the real primary vertex. In case of SOA collections, we can have SOA relations. Which themselves are SOA collections as well, and they represent the relations between two SOA collections. And similar to the regular SOA collections, for the SOA relations, we can add relation fields. So here in this case, I want to create a relation between tracks SOA collections and primary vertices with some weights. So I just create a table for the tracks and PVs, and then the same way, the way you would do for a regular SOA collection, here I'm using CMD, so I want to put the n number of them at once and just take the indices of the tracks, indices of PEPs, and the weights I want to assign to them. And this simply creates the relation. So far, I only mentioned how we access the information and how we create things, but in reality, we do much more complicated things. For tracking, you already heard, Andre, we do half transformations. In case of a combination of tracks, we do vertex fitting. This means you need to deal with a lot of matrices and more complicated operations. So our collections basically need to allow for these complicated calculations as well. So this is in principle not much different for SOI collections, but to take the full benefit of vectorization, we want to use the CMD instructions. The thing is that we don't really want to decide which architecture to use in advance. So we need to be able to have flexible code to develop while we're developing our code. And these instructions are intrinsic operations or vector operations. They depend on architecture. So what we do is instead we have wrappers that will allow us to switch between them. So basically what this does is you have one function, let's say called an exponent, and you want this to be able to call this for whatever architecture you are the same way. So the user will never know what you're using. They just call the same function. In principle, there are more generic CMD wrappers, but we decided to have LHCb specific wrappers. And there is two reasons. Main reasons here are as I said, when we develop, we don't want to fix which architecture to use, but in principle, we want to fix the instructions at compile time. This has the benefit of this advantage. It's less portable. So if you compile it for one architecture, you cannot really use it for another one. But this is not something really we want to do anyway. The benefit here is then because it's fixed at the compile time, then compiler can do much more optimizations on how to run things, and this has additional benefits. This is fully integrated in LHCb software, so for the users it's easier to navigate. We basically, for these wrappers, we have most of the common math functions and matrix operations for all architectures. And this can develop in time whenever we need something new, we just keep adding it. And additionally, for these whenever possible, they are templated, as I said, and templated for all backends. So for the user, it's just calling one same function, whatever, for whichever architecture you're using. So now the next thing, so we do have some, we created our objects. So we have a k-on-pi-on combination. We want to decide if this is a good combination or not. We can do vertex fitting, as I said, this is where the CMD wrappers come in. We can do much faster vector operations on them. But additionally, we need to select, for example, we want to cut on the mass, we want to cut on the vertex quality, or we want to be able to do operations on these candidates before we decide to keep them or not. And for this, we also improved the selection part of our software. So what we mean selection, basically, once we have the particles, we'll have PVs, and then we want to be able to do some association between them or some operations on them. So all these goes under the hat of selections. In HLT2, we have more than 1,000 exclusive lines. So each of them does a lot of things. And this, as I said, it could be different combinations or vertex fitting and so on. In run 2, this was about 30% of time spent in the trigger in HLT2. And in the run 3 at the moment is also around 25% and likely to increase once we have more and more lines added. What we do here is to also improve how we do these operations, and we develop what's called a throughput-oriented selection. So we have So this is shortened to Thor. So Thor functors, these are basically function objects. They are designed in a way that they can be either an object you can call or a function. So they're agnostic to the input and output value. For example, if I have a particle, I can call its vertex and create a vertex object, but I can also just continue calling for the position of this vertex or the x component of this position. So these functors are composable, and this makes the development easier. So this is actually simultaneously developed for old and new event models. At the moment, you can either use an SOI type object or collection or an old key container, so that they both work. But the benefit here, can just show you on this table here. It's a rather old, but still so here we are looking at the combining a kaon and 2 pion to create a D meson using different algorithms. So our normal algorithms with the key containers, combined particles, and n-body decays are rather slow. Once you go to a 4-particle combiner, this gets much faster. And depending on how you vectorize, you can go much faster, especially the fastest you would get if you do AVX2. The additional benefit comes here from how we do the compilation. So instead of using just-in-time compilation, we are here doing a functor cache. So basically, we define our functors in Python, and we built these, and during the compilation, all these go into a cache, and then later when we run, these are natively used in the application. And this has a significant. I mean, this you can also do for the old functors, but the benefit is much more for the Thor, because basically for the old model we didn't have to do any compilation anyway. Now, so we are here. So we went through the whole process and found the candidate that we think it's good enough. So now it's time to save this candidate to somewhere. There are 2 steps to go. So one is to if there's at least 1 candidate per trigger, then we need to save the decision that this trigger was positive, and this is saved. The next is to save also this B candidate itself to a file. So this is what we call the persistency of the data. There are 2 steps here as well. One is to filter. Basically, you might not want to save all information in the objects. Maybe you calculated the mass information where you don't want to really persist because it's offline, it's not only used. So there's some filtering step at here to decide what information in every object needs to be persisted. And the next step is to convert these objects to a more basic data structure. Everyone I showed this figure told me it's very confusing, so I'm not going to stay on it very long, but this is for the run2 events model. Every object, as I mentioned earlier, that is just a pointer. Every container has pointers to different objects there, and these are standard objects with different properties and so on, but we cannot really persist them as they are. First, they need to go to a format, basically a bit more basic data format, such that we can serialize them. And so they should look more like this instead of blocks in different places. And then we add them up to each other, basically serialize and then save to a file. We also need to keep the relation between different of the objects at the same time. Now for SOI collections, this is much simpler because they are already in a simpler representation. These are just arrays. And that's the whole point of this. For the SOI structures, this means we don't actually need to do the second step of putting them in a more simple format because they are in the right format already. And the other thing is actually for the first point I mentioned here to selecting and filtering, this is actually already can be done when we create our collections. So in case of an example here for a momentum of a track, when I create this field for it, I can also tell it how to persist it, how to pack this information to a persisted to count process to a file. So in case of here, I want to, this is a float field, and I want to pack this float as a short integer with some truncation. And I have another field where I had it for some reason, but I don't need it anymore. So I can just already tell this field, don't pack, just create it. I can also have some fields where I want to save it depending on the versioning. So I might have created these collections that during data taking, at some point we change how you do things, and you might have a newer version. So with the newer version, I want to pack it, but with the older version, I don't. This doesn't change really anything how you create your collection. So here again, I have my tracks and all the three fields that are three texts that I created. And then later when I can simply save these tracks to a file. This basically brings me to the summary. I just want to show you a bit how much we gain from doing all these usage of all these SOA structures. This is not really HLT2, this is HLT1, but compiled on a CPU. And it's rather old, so there are more developments coming. Just looking at every step, so here is basically the beginning, 2019, when we started to speeding things up. So in blue, you see a scalar event model, and we do full tracking in sci-fi. And then next step is basically what doing a bit smarter operations in tracking. So defining what you want to do. It's not really computing part, more the being smarter on physics. Here then the algorithm again, this is half physics, half computing, just making things in a different logic, basically speed things up a lot. And then you get a big jump from here, basically going from doing the vectorization and using SOA collect SOAs and in vertex vector and the reconstruction of PV. So this is just mostly a jump from a few algorithms. And this doesn't really stop here. So as I said, this is 2020, so there's more gain coming here. But this is very well demonstrates the benefit of vectorization. And we could actually do this other way around by simply turning off the vectorization. The throughput for HLT1 goes down by half. So this is also a nice demonstration of how things are working well.
Thank you very much. Okay, we have 2 questions already, so please go ahead.
I'm actually repeating Paulo's question from this morning. The data structure, the SOA collection. I mean, this is something which could be so much reused by other experiments. So is this something you could encapsulate, or is there any strong dependency on LHCb software?
I think it can be customized. I mean, the way it's written at the moment, it is customized for LHCb, but the software is public, and it shouldn't be that difficult to also use it for other experiments if anyone interested. I mean, there's no plan to make it open software as far as I know, but the software is open itself.
Is it part of Gaudi, or is it somewhere inside? Where is it?
It's an LHCb software.
It's inside LHCb. Is it inside Alan?
No.
I mean, I think the difficult part will be defining the metrics, arbitrary size metrics with the SOA. For example, if we have like a 6x6 matrix, then we need to write down all 36 lines for each member of the matrix. So if we want to extend it to the arbitrary size matrix, I think it can be a little bit problematic because C++ doesn't provide any the member unrolling with the for loop, or like Java.
Can I put my second question exactly to this? This is probably, I never understood this, but the argument that the data locality gets automatically better, I don't buy. because if you say these are all in memory in your chart, you say I first do all x coordinates, then y coordinates, then z coordinates. Now let's go to 10,000 space points. I have in memory 10,000 x coordinates and 10,000 y, 10,000 z, and then I want to calculate the radial distribution of 20 space points. So what I have to do is I have to jump around in this array, right? So where do I gain here from the locality? I don't.
Well, this is basically part of this SIMD. So we don't do all 1,000 tracks at once. You basically have, depending on your SIMD vector size. So you have 8. Then
But
they
your
are
collection, but the collection of your space points. If you say this is all my hits, let's not call it space points. These are all my hits. I have 10,000 hits, and I put them into one of these collections.
I don't think they are all together in the same place in the memory. You just have the
Are they pre-packaged in there?
Yes.
No, sorry, they're not.
They're not.
No, that's a design choice. So, I mean, you can indeed debate if it's better to make an SOA or SOA-OS or whatever, a double thing. But when this was constructed, the idea was you want to do a fast filtering on one content. So,
Yes,
and
in this,
so
if you say all x bigger 5, I agree with you.
and
Yeah,
you can fast filter things. So this was a design choice.
absolutely.
If it's then better for all situations, I agree with you.
It's one shoe fits all is, I think, always a difficulty.
There's another question in the back.
So my question is kind of similar to Andy's second question. And it may just be my misunderstanding. But when you went from the previous run 2 model to the SOA structure, did the speed that did the gain in speed come from the fact that multi-threading is then allowed, or do you gain some speed just from going from your run 2 structure to the SOA structure, even if you don't use multi-threading, for example?
We do typically comparisons when we do our comparisons, we do with the same number of threads. So typically the gain comes from the vectorization directly.
So you really do get a gain just from changing the structure to the SOA, I guess is my question. Like on slide 4, going from the top picture to the bottom picture, or I guess not top to bottom, but the array of structs to struct of arrays.
Yes, the recently I was actually working on one algorithm, just simply doing this, basically double and reduce the speed by half.
Okay, so that was going to be my next question. So it's a factor of 2.
Depends on what your algorithm does. So if it's doing a lot of calculations, that naturally speeds up much more. So it depends a bit how much vectorization you can do in an algorithm and how much time that specific function, whatever it takes. So it doesn't always do 1/2, but
maybe one comment to this multi-threading thing. I think the main point is if you have one of these SOA collections, you just allocate the memory in one block, right? And if you have just a collection of multiple SB vectors that are allocated separately, you always lock a thread with this allocation. This is why for multi-threading this is also useful.
Sure. I was curious because at SVNH we will not use multi-threading, but I was curious. We have a structure similar to your run 2 object, and so I was curious to know how much of a speed gain you get just from going from the top to the bottom. And then referring to Andy's first comment, yes, I would also second that it would be interesting to have this sort of common software.
I mean, this is header only. So this is essentially 5 header files or what.
Yeah.
So it's not. I
So
don't
it's
think it would be a
straightforward.
problem to make this public here.
as I said, the LHCb software is public on GitLab.
Sure, sure.
Any other questions? Nothing online? Okay, if not, thank our speaker again.